It's on green now. Okay, good. So this is a formula which is probably mostly one of the most useful in natural all empirical sciences, and also most errors which people do, particularly what is even in physics and engineering, but definitely in linguistic, psychology, and all the things, is because they're not using or abusing this formula. And this is something about checking your hypothesis by comparing it with the data. Okay? This must be a quantitative procedure, and which is difficult for some sciences, even for physicists sometimes. And essentially, we use this formula saying that this would be a hypothesis, or this would be a hypothesis, and this would be the data. Okay? So I may say, what is the probability that my hypothesis is true? Probability of hypothesis being true, given a given data, experiments, right? Of course, I must say that this is, if this is my H, then I would write it like this. I would say, this is the probability of hypothesis before I got any data, right? This one, times the quotient, the factor, which is so in a sense, this is the factor which shows me how changes the probability that under such hypothesis, what is the probability of getting this data, right? So in a sense, this factor could be larger or smaller than unity, which means that my data could, this is called prior probability. This is called posterior probability. Okay? And this is what data introduces a factor. That's what essentially chain rule teaches us, that Laplace said that probability theory is common sense presented as formulas, right? So this is just common sense, but put in numbers, and you know this movement on fashion of fascist data fascists in psychology. These young people of your generation and the previous one, who more or less start repeating all the classical experiments for which they were taught starting from undergraduates, and like 90% of them are irreproducible. And those which are reproducible are definitely outside of any statistical meanings of which it was ascribed, right? And this is, in a sense, all this more or less quantitative comes out of this data. Yeah, yeah. P E. Yeah, this is the total probability of this observed, and this is a probability under this hypothesis. It could be larger or it could be smaller, right? In the sense that it depends. Okay, and particularly if I have, if for example I make tests, what I think the best illustration of a simple power of this formula is a consideration of a drug test or COVID test or any test. Because the test usually distinguishes between two hypotheses, right? Drug user, not user, positive, negative. Okay? So essentially, it's something which, in this particular case, you can write that, okay, let's write separately. So P of H1 under this E, this would be positive COVID test. This would be you are ill with COVID. Okay? Good. That means that you need to write P of H1, which is the probability of given person in this population be without any taken test, right? So before you took test, you ask, what is the probability that a given person, it's very difficult to think about yourself as a part of a population. This is the most of errors made. But imagine that you already mastered this difficult psychological art. So this is the percentage of people who drug users or COVID positive or whatever. And what stands here is P of E under H1. And what stands here is P of E under H1 of P of H1 plus P of E under H2 probability of H2. Well, these are numbers given by, this is 1 minus this, right? As simple as that. And this is something which depends on the quality of your test. This is called sensitivity. What is the probability that if you are ill, your test will show it? Okay? And this is called specificity. It tells you what if you are not ill but still get a positive. It's called false positive sometimes, right? So it's specificities. Okay? Now assume that your what numbers I took for my COVID or drug test. Okay, let's say that you true positive 0.99 or yeah, and also true negative 1 minus, which means that the probability of false negative is 0.01. So imagine that your specificity and sensitivity is the same 1%. Okay? So this 1%, I mean 99% that your test will give you a result if you are ill, and 1% that your test gives the result if you aren't ill. Before we do computation by Bayes' formula, what your guess would be the probability that you are ill if you went and can test and it's positive? Okay, look at the formulas. First you do intuition by looking in the ceilings, but then you do intuition by looking into the formula. And then you start writing. Okay? So what I did not tell you, yeah, it's meaningless, these two numbers, until I give you what is actually in which stage of pandemics you are. And then you realize, this is what you probably read in newspapers and what for most people was totally mysterious, why tests were working so bad at the beginning and they were working better and better because people were assuming that somehow tests were getting better. Tests were getting the same. Yeah? But this changes a lot. Okay? So in particularly, let's take something. So this is your P of E H1, right? And this is your P of E H2. Let's take P of H1, I don't know, 0.5%, more or less. That was actually, before pandemics, when I thought it was an amount of drug users, not in LA, but, kind of in an average city. So let's take 0.5. Okay? Okay, good. Now let's plug the numbers. So, and of course, P of H2 is 0.995. Okay, so we get all the numbers. So of probability of you being probability P of H1 under a given E is equal to 0.05 times 0.99, and then you get 0.905. You see, this is pretty small, which means that this does not matter. Sensitivity of your test, when this number is so small, does not matter much. It's specificity which matters, right? Because this probability is large. Okay? Now plus 0.995, 0.991. You see, there is 0.99, 0.99 here and here, but this is twice smaller than this, right? And now you've got something which is 0.33. It's small. It's smaller than half, really. Those are real numbers, right? So this is really something which is important numerically. But I think it's also important psychologically. Right? Imagine that what normal people who aren't scientists or doctors or whatever make mistakes because they forget about this factor in kind of a normal speculation. For example, your hypothesis is that there is a vast international conspiracy to increase government powers in several countries. And what is your evidence for it? Is COVID pandemics. Okay? Now, if there is such a conspiracy, this is pretty high. It's reasonable to assume that if you have an international conspiracy, they would organize some kind of global event. And this is one of the global events, and its probability pretty high that it would be pandemics because, you know, and that's it. And that's where most conspiracy theories stop thinking, right? We're never thinking about this, how small is this factor before you see any COVID pandemics, because, okay? And this is essentially why I think it's also culturally important. Now, if I just compare two hypotheses for not necessarily exclusive, just this is something which is, again, this formula could be written. So imagine that I compare a probability H1 under E to the probability of H2 under the same E, right? And this could be written as two factors of course. A lot of creative hand waving is made by rewriting chain rule in different ways, and then you can write philosophical tractates about it. But I actually use this formula for us physicists to reflect on ourselves and on a way that we use what is called a Occam razor. You know what is a Occam razor? It's something for which kind of a part of a religious dogma for physicists and for engineers too, by the way, is that if you have different hypotheses, you choose the simpler. If you have different computational scheme, you choose a scheme which has fewer parameters, right? And essentially, this is right, and this formula quantifies it. But it has two parts, and I call this first factor theoretician's factor. That was theoretical physicists use. And this is experimentalist factors. Well, this is simple. Theoreticians usually say that when you estimate your priors, you use beauty or symmetries or whatever. You prefer something which would be, but which means that you estimate probability as according. It is something which is not necessarily trivial. It's something which is a result of our long experience, and there are many currents, you know, which run under this river. For example, you say that if I have a model which is kind of very symmetric and very universal, it's usually a limit of many different models. For example, you take long wave limit, and it's usually you either have acoustics, you know, omega proportional to k, or you have omega proportional to k squared, depending on which class of symmetry. Or you would have, you know, Ising model. So in a sense, many simple models come out of as a limit of vast classes. So you expect their probability to be larger. But how experimentalists argue that for simpler hypotheses, this would be that if H1 is simpler, why the hell its probability will be? Probability of data under it will be larger than probability of data under more complicated hypotheses. What logic is behind it? As a use, this is the logic which people in the lab use every day, right? And it's logic which goes more or less like this. So if you have on a space of data, somehow the difference between a more complicated hypothesis that it's usually describe a wider set of data, in principle, okay? So it is something which it has more parameters, or it has a wider, so it's kind of, it's very loosely can be defined by some, this is a P of, oh my God, there are, okay, so this is my P of E of H2. And a simpler hypothesis is usually works on a kind of on a more narrow interval of data. They are both normalized, right? Which means that, so if your data happen to be compatible with both hypotheses, namely kind of lying somewhere here, I don't know, that's your data that you received. Then the simpler is usually have more probability. This is a mental picture, but it's not only something which describes you culturally what happens. It's how it actually could be quantified. Okay, so you say, okay, look, this is works on this space of parameters, and on this space of parameters, it could be quantified again as an entropy of this distribution, entropy of this, and then what is this overlap? So it is this factor which is essentially quantifies Occam's razor and its use. Sometimes in data science, people prefer to call it a minimum description condition. So in a sense, you should prefer the hypothesis which communicates the data in a lesser number of bits. Again, this is something, as I promised you, we're learning to look at different things as messages. Okay? So this is a suggestion, and indeed, so you essentially say that you communicate in this number of bits what is the hypothesis, and then you communicate within this hypothesis, given this hypothesis, a given data. Which technically means that you say, okay, my hypothesis is that this is Ising-Hamiltonian with, I don't know, with this set of constants, right? And now I interpret my data. For example, people use Ising model very effectively to describe the pair correlation between neurons firing in our brain, because this is, neuron is a spin, right? It either fires or not. So it's a two-state system, and you can describe it as an effective Ising model. What you need this Gij, the factor. So this would be your data. So you communicate it within this hypothesis. Of course, this is essentially a logarithm of P of E and H, right? This is the same chain rules, right? And the statement is that you prefer shortest communication, again according to this rule. Okay, so what I'm just wanna show you is that this simple chain rule is used culturally, but also quantitatively in a very direct ways to choose what kind of hypothesis to use, what kind of communication scheme to use, what kind of, how many parameters to choose if you're able to question it.
When you say simpler, is it saying that entropy of evidence outcomes is lower?
Yeah, it means that you would use shorter words for communicating this data, less symbols. In 3 lectures from, maybe in 4 lectures from now, we'll discuss how to play stock market. And then what you will discover, but for this I will need relative entropy, which I will introduce in 5 minutes, you will learn the following things, that the person who is able to encode a given set of market data shorter will get more money proportional to how much shorter he can do it than other players on the market. Okay? It is something which tells you that information is not only energy in watts for Carnot, it's also money. But this is again that the shorter you can encode it, the more efficiently you contain the data, the better you're able to predict. Okay? But here, I mean, this picture, I guess, is self-explaining, right? So that really, if you're working within a scheme in which is concentrated in a more narrow interval, and your data happen to be in this interval, then you prefer this, because it has more probability for this data, according to this formula. Okay? Good. And the last thing which, again, I want you to call your attention is the subtle shift when we went from this trivial formula, which is just combinatorics, to this formula, which is about prior and posterior, and it is about expectations. A standard probability theory appeared, as you know, out of gambling and then mathematicians, and it was always treated probability as frequency happening in reproducible events. When we were kids and we were learning this thing, we were always throwing a coin, mentally assuming that the coin is the same coin and the probability would be about these events, right? And then when we hear that the statistical the probability of our Earth having, you know, CO2 over here and there within this class of model is 0.2. What the hell? Well, we don't have ensemble of planet Earth, and we cannot run different scenarios of global warming, and they say that within this class of scenario we'll have this probability. What we do, we use the Bayesian framework, which treats probability as expectations, and that's why mathematicians also later adopted the value for a mean value as expectation value. And what it teaches us is how to update our expectation according to the data. Okay? It's very uncomfortable for many people because it assumes that you do science which is subjective. This is something which took hundreds of years really to accept the simple fact. There is no prediction without assumption, and there is no inference, no reaction on the data without any assumption. Now we have experimental evidence, for example, that if you open your eyes in a dark room and you start getting visual information, then you may expect that from your retina there are signals running to your brain. And that's true, they run. But you can also measure that it's about the same amount of signals running from your brain to the retina. What they're doing? There was no information before. They're predicting. They're predicting what you expected to see and then comparing what you see with what you expected to see. But people knew it in the 15th century. There is a famous experiment which Italians did about binocular rivalry. You know what is binocular rivalry? You know. That you do it like this, and you put here a dog, here a cat, or I don't know, whatever, a girl, a boy. And then you ask, what do you see? Yeah, just put different. It's stays sane when you're playing it at home, but it's really very interesting. What they notice is that sometimes you see one, sometimes you see another. If you have seen many, many boys, then you won't see girl. It's called priming now, okay? Which means that, but this is a signal. Your retina gets image. And it's get into the next, I don't remember how you call it, I mean this first processing level of ganglia, yeah? It gets there, signal gets there. Just brain doesn't disregard it, right? So it is something which is really, we always predict. For example, if you sit two numbers, and somebody asks you, what is the third number? What would you say?
30.
Huh? 30? 5, 8, 30. What is the rule? So what is your hypothesis? What is your hypothesis of the world?
It's an addition of the previous numbers.
Ah, 13.
Yeah.
Okay? But this is not an addition of the previous. So in a sense, you were given two numbers, so the only thing which you can surmise what is how you get from here to here, right?
Then I would say 11.
That you would say 11, okay? And this is what kind of, engineers or accountants would say, well, they are arithmetic sequences that you mostly see. Yeah, but biologists would say 13. Why?
I'm a physicist.
Because it's Fibonacci. And in nature, you see much more Fibonacci numbers. I mean, just go, every pine forest gives you these pine coins, right? So if you happen to get 12 plus minus 1 from a noisy channel, your choice would be according to your prior, right? That's how it works, and what we need to accept it. Okay, so enough with philosophy. Let's go back to computations. Now, what I want to talk is what happens if this sequence is actually a sequence of, on average. Again, this is it's kind of monotonically decreases. So it's something which disproves your hypothesis, right? Because essentially, what is the idea here that if you want to prove your hypothesis? Of course, it depends on the prior. But do this experiment many times, take logarithm, like in everything we do, we take logarithm of and you will see that this is stop dependent on it. You really need this increasing. Like in the spirit of renormalization group, we believe that as we do something many times, it would go into some probability which will be a fixed point of the flow. But it could be 0, in the sense that our hypothesis is not true, and data shows that it is not true. And now the question is, how fast? And this question, how fast, or how many data we need to gather before we conclude that our hypotheses weren't true. Let's say that our hypothesis is about distribution. So the true distribution is P, whatever, of some numbers. P1, Pi, Pn. But we assume that this distribution is Q1, Qn. This is our assumption, right? And now we want to actually estimate this factor which tells us how every data, again, what we'll be doing, we'll be getting n sequences, long choices out of 1, 2. So there is some symbols, right? Some kind of A, B, Z. So they all have different probabilities, but we assume that their probabilities, what more they learned from the print show, but they're actually a little bit different. So the question is, how many experiments we need to disprove our hypothesis, namely to have this factor, let's say, be 10 minus 3. So like 1,000 times we decrease whatever prior we had, it now 1,000 times less. How to get it? So how to get this factor? If we know two things, we need to just compute it, right? So what is the probability of course we cannot compute it for arbitrary sequence, but we could compute it for which sequences? So we have a sequence of object letters, for example, right? With which sequences we work over and over and over again in the limit of n going to infinity, where n is not this n, where it's a number of alphabet but we'll have some like symbols a, b, k, z, l to n times. So when n going to infinity and we have a string which is long n, so which strings we only consider? Typical. And when we consider typical string or typical sequence, we know how many times this would appear, right? And how we would know it? We would know it from our probability. But our probability is q. And in reality, they appear with probability p, right? So we would have symbol number I appearing that number of times. We look at it, it appears that number of times. That's typical sequence, no way to escape it, right? That's how much time it appears. But for us, well, the probability of it is that it actually appeared, each one with the probability q. And because each appearance is with this probability, and it appears that number of times, that's a probability, right? Each one independent. So what now I need? I need now to make a product out over all I, right? And of course multiply by ubiquitous n factorial divided by pi n factorial product of I. Yeah? So this is a combinatorial factor where they all can appear. And this is a probability which we judge that they appear, right? Okay? Now, this is a true factor. Okay? So this is a, and now, of course, I would put everything of it into the exponent. And I would say that this is an exponent. And yeah, of course, I will be using sum over I. So when I put this into exponent, I would get logarithm of q, right? You see? So I would have p log q. And this is the standard stuff, which I know that this is an exponent of n p log, no, in this case, logarithm of p, right? Okay, so this is the standard Stirling factor, and this gives me p log q, right? One with a plus, another with a minus. And so, as I promised you, we now see something which will appear over and over again. Okay, and again, we're interested in the exponential rate, right? So we expect, and this is the, what we obtain is precisely what we need. It's a probability of EH divided by a probability of E. This is our Q distribution. This is our set n string letters, right? And we now seeing how fast it decays with n if our Q is not equal to P. First of all, it's zero only when all Q's equal to all P's. Absolutely. The moment that two are not equal, and the sum of all P's is unity, and sum of all Q's is unity, this is non-zero. Right? Moreover, it's non-negative. This is something needs to be proved. We will prove it because the mutual information is non-negative in this particular case. But and this quantity, it's a generalization of mutual information. This is kind of a last, well, except quantum, this is the kind of most sophisticated, well, not, there will be one more, but much less useful. This is called G, P, Q. But generally, you know, I sometimes forget this to us. This is not P conditional on Q, right? And it's not P comma Q because it's not symmetric, right? I don't want to write it D function of P and Q because you see P and Q stands differently here. First of all, it tells me that it's not a distance in the space of distributions, distance is symmetric with respect to. Yeah. So neither it's a difference between entropy. It's not P log P minus Q log Q. It's totally non-interesting quantity. It's just how much more uncertainty in this distribution than in that. It does not compare them. This compares. It has important properties of distance, namely that it's non-negative and it turns into 0 while all P's equal to all Q's. It's called relative entropy. Of course, this is a rate, right? Per symbol, your probability decreases that fast. And jumping ahead about encoding, that when we'll be playing stock market, I will show you, this is the famous Kelly formula, that it is, if this is your opponent and this is you, that's how fast your earnings would grow with this exponential rate, right? And so it's sum over I, pi. In bits, it will be log 2 pi's over qi's. Okay? It's also, because it's such an important quantity, it's still sometimes called by the guys who introduces Kullback-Leibler. Not Stan Leibler, who is now in Princeton, another Leibler, but more kind of, it's called relative entropy. Okay? So here we now introduce this really important measure, and we now slowly start applying it. Now, why mutual information is a particular case of relative entropy? Is it visible? Let me write mutual information I it's essentially the way I wrote them at the very first time when we introduced them. There is nothing new here. We wrote all this. I just want to remind you, okay? So our mutual information could be written like this, which is essentially a conditional probability divided by this. But we can always write this conditional probability by a chain rules, right, as a joint probability divided. So we get this. This would actually give us the symmetric form, right? It's a joint probability divided by the product. Well, call it a Q, and that's it. It's a relative entropy for a very particular case, where our hypothesis is about independence. So what mutual information does, it compares true distribution with a hypothesis about independence, and then it's a measure of correlation. Relative entropy generalized it for any hypothetical distribution, right? So in this respect, it is just a more general object, right? And then there are many creative uses of one and positivity another, etc. Will be used, okay? But is that clear how this object appears, right? Most important mental step here is that you see the data that many times, but you treat it you perceive it, you ascribe probability to it with this. And then as this probability goes to 0, you actually abandon your hypothesis which come out of here. Okay? Question. Now, we all do this with typical sequences and get used to it. It's now almost religious belief. But now we can ask how wrong is our asymptotic equipartition. Let me remind you. Or the statement that all long sequences are almost equally probable. Yeah? All events are almost probable. You remember it? So we took a sequence. We look how many every letter is there. We treat this as a probability. So we treat observed frequency as a probability, computed entropy out of it, and says that the probability of any n sequence is exponent minus ns of q, what we observed, right? So we observed frequencies q1, qi, qn, and we treat them as a probability, right? Now, we have finite sequence, and in a finite sequence, generally, nobody says that these numbers are already equal to the true numbers which exist here, right? So, what is the true probability of observed sequence, right? So if we have, this is a p which is true. That's what we just observed. What we expect, that what we look at a given sequence, the finite size, and we observe some numbers. Out of these numbers, we compute their entropy, just qi log qi, and say, okay, this is a probability. As a true probability, again, on average, taken over many, many such finite sequences, what do you expect? That the true probability on average is like this, on average is a little bit smaller, or on average is a little bit larger. What's your intuition about it? Think about it. It's computable. We'll compute it in a moment, right? Because we assume that we know this number, we know these numbers, we now just compute and compare. Again, we use our favorite tool, which is asymptotic equipartition, and treat in typical sequences. And now we ask, okay, but if it's finite, then definitely our Q's are a bit different from P's. It's analogy enough to get an answer, right? They're a little bit different. And what this difference would make us underestimate or overestimate the probability, or just on average it will be the same. Somehow the positivity of relative entropy must play the role here, right? What's your intuition? Let's compute. Okay. We observed each symbol n qi's times. That's what we observed. I'm actually turning table with respect to this argument which we made here, right? Because now, before we assumed something, but what we observed was a true probability. Now we observed something, and this is what we observed, right? But what is the true probability of it? It's pi in this power, right? Okay? So indeed, not what we guess, but a true, I mean, God Almighty, or if we would do more and more and more experiment, if n would be really increasing, then we would see how this number would actually be closing to this number. Okay, and again, it will be a product of this thing, and then it would be, I can write it as exponent, or I don't know, 2 if I will be doing everything in logarithms, n sum over I, p, q, this is q, right? And the logarithm would be now of p. So it will be q i's log p i's, right? Let me add here plus q log q and me minus q log q, right? So that I could present it. So the true probability is exponent minus, well, q log q is my entropy, right? So it's minus n s of q. That's what I assumed, right? That's my asymptotic equipartition. But then there is this guy, which is minus g q p. So it's q log p over q. It's non-negative. It makes it smaller, it makes it larger. The true probability is larger. I'm actually underestimate. It's something which appears in many, many things. When we will be discussing renormalization group, we would also ask about things which happen in subleading terms. What actually happened, not in a thermodynamic limit and going to infinity, but a little bit a subleading term to it. What is its sign? And it's usually that when you work with a finite sample, you don't see some correlations yet. It all appears a little bit more random than it is. This is something, a general lesson. Again, there are, it's not something which you can trivially kind of claim. But in this particular case, the fact is that, and again, it's finite, right? Because it's all the effect of finite n by which these two things are different. Because again, we know that this q and p approach each other exponentially fast. It's a law of large numbers, right? So when n increases, so this is also dependent on n. This is a subleading term, right? But it's always of the same sign. The true probability is larger. We a little bit underestimate it, okay? It's an important qualitative lesson, I think. Is that clear? This is pretty elementary consideration, right? And again, I want to call your attention to what we were actually doing. Here and here we were doing the same. We were saying what is observed and what is the probability that you estimate, okay? Or what is observed and what is the true probability according to the true distribution, okay? Good. Questions? Good. Okay. Now, let's see what else. Yeah, now probably I mentioned several times non-negativity. Let me now show it in a simplest way. So we have, let me write minus d of p q. At some point I stop writing here two things, but you'll remember that the moment it's d, it's never conditional, right? It's just, so it's sum over pi log pi over qi. Now I would use, probably I would use logarithm for simplicity. So logarithm of x is less or equal x minus 1, and the equality is actually, so if this is my log, and this is my, so the equality is only at x equal to 1, but generally log is always less. So I can write this as a sum of over I of qi's minus pi's, right? And this is 0. Oh, this is unity and this is unity, right? So this is as simple as possible proof of non-negativity, so that, and the moment that this number are stop being equal, then you have this strict inequality, because this equality logarithm x and x minus 1 is only when x is equal to 1. Okay, so this is kind of a simplest way to see for any numbers, right? But you see how powerful consequences it immediately has. So it is this p log p over q, something which we will see in quantum case, of course, too. But it's really, you look tired already. You're still functioning, because for this you need to complain, ask questions, whatever. I need to feel that you, okay. Now it's, maybe I'll, yeah, we still have some time. I'll show you again application of this quantity to something which we already discussed, namely the encoding. All right? Yeah.
So you just mentioned that since dpq is different from dqp, what is the actual?
Well, but they're both positive. You know, because this is just a notation. The moment you have p log p over q, this is a mathematical statement. I have a vector p and a vector q, right? Two vectors of the same length. The sum of pi's is unity. The sum of qi's is unity. Sum over j, pj log pj over qj, less equal than 0.
I understand. So, but I'm saying is.
And it's strictly negative if at least one number are not equal.
I understand, but what's meaningful in this calculation is dqp, right? Is dpq.
Yeah.
Is that
What
really meaningful?
what here I express it not in terms of pq, but qp. You know, it's always why there is no symmetry in this. Why this is asymmetric? Why is this not a distance in the space of distribution, right? Because there is no symmetry between reality and your assumption about it. That's it. It is that simple, right? But in this case, the reality is q's. That's what you observe. You say, but if there is some true hypothetical p exist, which appears in the limit of large, then it would be this expressed in terms of this, right? But it does not matter. It's still positive. Okay.
My question is very simple. dpq is not actually a meaningful quantity right now, right? Only dqp is.
Well, it's also meaningful quantity, but it has no relation to the following questions that I'm trying to answer. A given sequence with a given q's, is it more probable or less probable according to my asymptotic equipartition estimate? Okay, so this is actually teaches us what we did, where it was estimate from below or from above. We say when we see a very long sequence, we estimate its probability, which independent on specific letters. We just take frequencies over there. We don't care in which order they appear. Just take frequencies. According to these frequencies, q, we calculate S of q and say, yes, this is a probability. What I now have shown that this is from below. This is an estimate from below. Because no matter in where these q's aren't equal to asymptotic frequencies which appears in the large limit, this answer will be larger, the probability. Okay? It's a very powerful statement, right? And simple. Okay? And it because this asymptotic equipartition is all our thermodynamics, if you wish. All our thermodynamics essentially kind of based on this ensemble equivalence and all this. Okay? I see you, you awake. So ask. This is something which is technically extremely elementary, and yet it's not well, it is elementary, like it's just elementary function. There's no even matrices or whatever will come, but I'm trying to use the most elementary mathematics here, because this really, the difficulties here are mostly conceptual, right? Okay, good. Now I want to return and use this. This relative entropy will appear now at every lecture. That's what I can promise you, maybe in every second lecture. So now encoding. I want to return to encoding and treat the following problem. That when we were, you remember treating this A, B, C, T, this four, there were, of course, probabilities chosen in such a way that they were powers of 2, right? You remember there was 1/2 probability, 1/4, 1/8. So when I took a log of it, that would be 1-bit symbol, 2-bit symbol, 3-bit symbol. Well, reality is, of course, more harsh. And we say that, yeah, you need to take, for example, you have probabilities of your symbols coming with this one, so you need to encode it, you know, so that it would be the shortest using for most probable thing and the longest for less probable thing. So you need to take logs of these guys, and that would be your essential, this with a minus, and that would be length of the word which you use for a given symbol, right? So this way you can achieve maximal compression, and then your rate of information transfer would be the fastest, namely your mean word would be the shortest when you average over, when you take mean L, which is the sum of PA L A, which is of course will be minus PI log PIs, and this would be your entropy, and you will be happy because this is your asymptotic rate. What reality corrects here? When my PIs are not powers of 2 negative integer power, is that these are non-integers, right? If you take logarithm of 0.3 of 1/3, this is not, unfortunately, a logarithm by 2. It's not, unfortunately, an integer number. So you need somehow to, to use a closest approximation, which you often can say, okay, just let's take, I don't remember how, like this, yeah? So let's take the closest integer to it, and let's call it a day. Yes, question? No, this was the operator is. So, but this won't be now exact, which means that now we will pay a price that our rate of information transfer would be equal to entropy, right? And unfortunately will be less, which means that our length of our world will be on average longer than we would be wanting this way. Okay, so now if you say that we have an alphabet I runs from 1 to D. Actually, from now on, and if I will be using n, you would better correct me back to D, because it will be our dimensionality. I mean, kind of when we move to physics back to, so I would rather use D, okay? So now, if I would say that I have some Li's, now I have a set of Li's, and then I could divide my Qi's as D in the power Li divided by sum over I of D in the power Li's, right? So for binary, when I hear and in the D alphabet, of course, this would be if in my alphabet not 2 symbols but D symbols, then my everything must be computed like this. And L in the power D is my probability, but now it's not a true probability which standard here, it's some kind of Q's, right? So essentially, when I'm using a specific set of L's, whatever they are, this is their effective probabilities with which they appear. You may prove that this set would be restricted by 1, but we may assume that it's really I can find such else, that the sum of d in the power else is 1. So this would be just d minus LE. That would be my effect, my probability, which I really use. Okay? And now I may, with this probability, compute the mean length, right? If I would working with this probability, and my L would be logarithm of this, but they aren't. So what I will get, I would get that L mean value is a sum over I of Pi with Li. Pi is truly 1. So this is a minus Pi, but L is log d of Qi's. But this Qi's is this one, which I can write as P log P minus log P over Q, i's. Okay, and the sum and the minus. Which would mean that this is S of P, which is this quantity, and unfortunately plus d of P Q. You see, again, Q's what appears because my L's aren't exactly logarithm of P because they must be integer. Then what is your, and that I already mentioned it, but now we understand where it comes from. Of course, this is now L is always larger than S of P, right? Because my relative entropy is always non-negative. But what one can show, in particular if you take an integer, the closest integer value, that it's always less than L, that S of P plus 1. So your D is restricted by 1. Because it cannot be larger than 1, you already took the closest integer, right? You don't go away from it. So, but now we understand why it actually appears, because this is integer, and PI's, logarithm of PI's are generally not. Okay? So this is, it tells you that relative entropy measures the price of imperfect encoding. It also measures the rate with which you invalidate your hypothesis. As any other thing, mutual information, entropy, also relative entropy, is something which stands in the exponent multiplied by n. It always per symbol, right? And what stands, because it's a mean length of a word per object that I encode. This is my objects which I encode, and I encode them by different lengths of words. This is my mean length of a word. The shorter the length, the more is the rate of information transfer per symbol, right? And the relative entropy measures in exponential rate imperfection of this being integer. Okay? Questions? Remarks? Okay. Maybe last thing for today is monotonicity, and then we'll call it a day. We'll won't have problem of monotonicity in the second set. Anyway, we'll push it to the third. We'll see, because you're giving it now for 2 weeks. Okay. Anyway, I'll introduce it now, and because we still take a deep breath, close your eyes, relax for 2 minutes. Something which is necessary. We're already over 2 hours. Okay. So now, what I want to discuss, and which is, it's in a sense starts a subject with which we'll be returning, it's what happens when you eliminate variables, right? So you kind of, let's say, your probability exists of some xi and yy. So your PIs are kind of two-dimensional, right? It depends on the two sets of symbols, and so you are interested in the relative entropy between two distributions. Now I won't write because now it's clear that, and it is Q of xy and yy. And again, you can guarantee that this quantity is non-positive if there is at least one pair xy for which probabilities aren't the same of P and Q. But now you're interested in the following thing, that you just take, you remember what we call marginal probability. So P of xy, it's a matrix. But if I sum it all over x's, I would get P of y. It's something which stands on the margin. Or if I stand, so if I really define P of xi as a sum over j of P of xy, yj's, then I may ask how this is actually related to d of P of xi, q of xi. Again, defined in the same marginal way. Okay? So if we observe less variables, what we expect our relative entropy, or it could be larger, it could be smaller. Do we expect any definite inequality between these two things? Intuitively first, what do you expect?
If I have more variables, I expect that I am closer to the, so D on the left side should be smaller than D on the right side. I expect
You add to D every time you find any non-coincidence.
So I have information about, I have an extra variable on the left side. So I have a better way to.
No, but I'm talking about the quality of approximation. What we did, we took one matrix, which is P ij. Okay, so this is x i's, and there is x goes this way, and y going this. Well, actually, this is x, this is y. So you have a set of numbers, right? One, and this is your P, and then you have another set of numbers. It's Q.
I compare them.
Just two matrices, right? So now what you do, you just sum. I mean, what is this D tells you to do? It tells you sum over all ij, your P of xi yj, your log of P xi yj, divided by Q of the same xy yj. Every time you find in this matrix the number which exactly in this place is different, gives you something positive on a sum. There could be positive and negative, but they sum by convexity into positive quantity, right? Now you say, okay, forget it, just let's sum it over here. So I get sum over here and I get sum over here, marginal distributions, okay? Is there a chance that there will be non-coincidences here generally larger or smaller? Because any non-coincidence contribute.
Yeah, it's larger. Like
Which one will be larger, that one or that one?
so if I add them, it's more probable that they will start differing. P and Q.
That which start differ or stop differ?
Start.
Huh?
Start. Like,
Start differ. How by adding the same numbers you can get different numbers?
no, what I'm saying is that like I had certain numbers and then so if they were different to begin with in certain places.
They were different to begin with. Let's say these numbers, this was larger and this was smaller.
Yeah.
But as we said,
You're
this is a probability distribution. which means that somewhere here there was another number which was smaller. But it could be not here, it could be over there, so there still will be difference, right? But it could be exactly here that this would be larger. So when you sum it,
Comes closer.
they would be the same. Over here on a margin would be the same. Because this difference because every time this is smaller than this, somewhere must be larger, right? This is the beauty of stochastic matrices, right? Okay, I'm not proving this to you. I am kind of, doing lap dance, which convince you that it is so. But it is, I really want you to see how it works. Of course, it's always like this, and of course, it could be formally proved, not only, but the meaning of what all this convexity is, it is like this. It's all come from the fact that the sum is unity, okay? Whatever you do, it's sum to unity. So when you sum things, generally, you can't create differences. If you sum the same numbers, you get the same numbers. But you can sum different numbers and get the same numbers. This happened, right? So essentially, this is a simple explanation. This is quantity, and this is called monotonicity. So when you will be, if somebody would be studying a more formal courses, they usually introduce this in a pretty abstract way. By the way, there is pretty good, very short, like 3 maybe lectures by Witten, who gives this in a very, very compact, pretty formal way, but extremely lucid and with much less, extra things. So monotonicity there is a kind of a central object over there, right? Now, let's make one step further and then call it a day. So that essentially tells you that extra information does not hurt, right? But which means that you add here something, you see more difference. Because essentially this is something which is your instrument to proving that your hypothesis is not true, right? This is a quantity which the larger it is, the less experiments you need to do. It costs, you will see in Kelly's formula that it's just money. It's a rate with which you waste money or you earn money, right? Indeed. Because look, the question is very simple. How many experiments, how many data you need to gather to disprove your hypothesis, right? Of course, if you can observe more variables, it would be faster, and D would be larger. That's the essential message. And yeah, maybe the last thing that I tell you is what happens when you add third variable. That will be probably enough for today. We won't add more variables. So imagine that now that we have some q, which is x, y, z. So I have 3 variables, but there is some true p distribution, but my q is a hypothesis. Now I'm starting to use this fact which we mentioned, that mutual information is a particular case of relative entropy when I factorize the distribution. So what I now want to take just a particular q which says that x is independent on I don't know, p1, p2 of y, j, z, k. Okay. So I essentially make a hypothesis that I neglect correlation between x and the rest of things. And then again, I am asking, what if I measure the relative entropy between true p, x, y, z as it is, and my q, which is z, okay. I look at it and I say, now this is some relative entropy between the true distribution and this distribution. But I want to do the same trick. Namely, I want to ask what happens, what kind of monotonicity exists or not exists, if I consider it just p of xy between q of xy. Of course, q of xy, by definition, well, P of x, y means sum over all k, P of x, y, z, k, right? And the same q. So essentially this q is just P1 of x, P2 of y. I just sum it over k and get it over here. So now what I'm asking, if this is now something which is more or less like here, but for a very particular combination, right? But now you see that Q here is a product. This was not a product because this is not a product. But after I summed over Z, my marginal distribution of y, just a marginal distribution of y. So this is a mutual information, right, between x and y. Just by definition, right? And I know mutual information. So let me write it down. So now I can, where I did it, so I would say that this is and s of x plus s of y z minus s of y s of x y z. Okay, so this is this d is this is my this quantity which is and I'm now trying to so this is my left side and my right side would be this, which would be s of x plus s of y minus s of x y. Okay, so what I now wrote, I wrote this in terms of this d is this minus this, and this is this. So what I do, I put right signs everywhere. No, it's already so this is s of x plus s of y minus s of x y, right? And this is s of y z plus s of x minus s of x y z. Okay, so this is essentially what I wanted to write. I'm also tired. So this right hand side, it's my mutual information, is s of x plus s of y minus s of xy, right? And but this is kind of, again, I can treat it like s of yz plus x minus s of all of them, right? So essentially the monotonicity applied to this object now allows me to obtain a non-trivial relation between entropies, because this object now turned into and this will be sy will go out, and that's what I wrote without derivation. So let me write it and finish on it. This is the following statement, that s of xy plus s of yz minus s of y minus s of x y z, and we'll start next lecture from it and discuss the non-trivial correlations between three objects again, as I said, physicists like to think in twos, right? This correlated with this, uncorrelated with this. The moment there's a PS3 object, then the third object influence the correlation between these two, and it could influence it in different ways. And this is a very powerful inequality which helps us to sort it out. But I'll probably end here without torturing you further. Okay, see you next week, and